Hey there, welcome to the Science Salah Lotfy Channel. Today I've got an incredible story from Egypt, one that just might change how we build our world. Imagine turning two huge environmental headaches, cement kiln dust and polystyrene foam, into something we actually need: strong, lightweight concrete bricks. Sounds wild, right? Let's break down the science. First up, cement factories. They're essential for construction, but they leave behind mountains of cement kiln dust, or CKD. Every ton of cement makes about 0.7 tons of this stuff. Add in polystyrene foam, the white, squeaky packaging you see everywhere, which basically never breaks down, and you've got a recipe for disaster. Or maybe for innovation. Researchers at Al-Azhar University and the Egyptian Atomic Energy Authority asked, what if we combine these waste materials? Here's what they did. They dissolved polystyrene waste in regular gasoline, making a gooey liquid called liquefied polystyrene, or LPS. They mixed this with CKD in different ratios, aiming to create a new kind of concrete. The sweet spot? 30% LPS with CKD. This mix reached a compressive strength between 2.6 and 2.7 megapascals. Porosity dropped to just over 51%, and water absorption was around 42%. That's pretty impressive for something made from trash. But the team didn't stop there. They added even more waste, like Portland cement, iron slag, and waste glass, trying out different combos. The best results? 15% additive gave the bricks even more strength and less water absorption, perfect for non-load-bearing walls and insulating bricks. To make sure it all worked, they checked the mix under a microscope. The LPS filled the tiny pores, with no cracks or weak spots. Chemical analysis showed the new mix was stable and the plastic played nice with the cement. In simple terms, the liquefied plastic acted like super glue, holding everything together. So, what's the big takeaway? This research proves we can turn two big waste problems into a green, affordable building solution. Instead of filling up landfills, we could be building the cities of tomorrow. That's a win for construction and a win for the planet. If you enjoyed this deep dive, don't forget to subscribe, like, and share. I'm always here with more science that's shaping our world one idea at a time. Check out the video description for the original research paper. Thanks for watching.
Hey everyone, welcome to the Science Salah Lotfy Channel. Today I'm diving into a groundbreaking research paper that's all about turning trash into treasure, specifically how we can fight pollution and recycle waste using advanced concrete technology. Let's set the scene. This paper is titled Sustainable Lightweight Concrete Made of Cement Kiln Dust and Liquefied Polystyrene Foam, Improved with Other Waste Additives. It was published in the international journal Sustainability Volume 14, article number 15313. The timeline: received November 2nd, accepted November 15th, published November 18th, 2022. And it's out there thanks to MDPI, the big Swiss publisher in the academic world. Now meet the team behind this innovation. First up, researcher Abeer El-Sayed from the chemistry department at Al-Azhar University in Cairo. Then, professors Dr. Abeer Faheim and Dr. Aida Salman, also at Al-Azhar's chemistry department. And leading the charge is Professor Dr. Hosam Saleh from the radioisotope department at Egypt's Nuclear Research Center. That's a powerhouse combo. Top scientists from one of Egypt's best universities and its top nuclear research hub. The paper was handled by academic editors Jiming Ma and Chaofeng Liang, both experts in sustainable materials. A quick note, MDPI, the publisher, keeps things neutral with affiliations and geography. And good news, the article's open access, so anyone can read, share, or adapt it as long as you give the right credit. Now what's this research all about? The authors came up with a way to make eco-friendly lightweight concrete by mixing cement kiln dust. That's a big industrial waste plus liquefied polystyrene foam, which comes from old plastic packaging. To beef up the concrete, they mixed in iron slag, waste glass, and a bit of Portland cement. Their results? Bricks that are light, insulate well, and are perfect for non-load-bearing construction. Instead of sending toxic waste to the landfill, this method gives trash a second life and helps make construction way more sustainable. Bottom line, this paper is a huge step forward for sustainable material science and shows how teamwork across fields can solve real-world problems. I'm honestly excited to see Egyptian scientists making a global impact. Want to read the full article? Check the description below for the link and citation. If you enjoyed this, hit subscribe, like, and share. It helps out the channel and brings more science your way. Thanks for watching for Science Salah Lotfy, where science truly meets purpose.
Kiln dust, or CKD, a dusty powder left over from cement production. Every year, cement factories generate about 76 million tons of CKD, enough to fill countless landfills and pollute air, soil, and water. Meanwhile, we're drowning in plastic waste, especially polystyrene, the lightweight foam used in packaging. Polystyrene is tough to recycle and can linger in landfills for centuries, polluting our environment. Globally, we produce over 400 million tons of plastic waste each year, but less than 10% gets recycled. The rest piles up in landfills or ends up in nature, harming wildlife and ecosystems. Imagine if we could tackle both CKD and plastic waste at once. Scientists are asking, what if we could combine these two massive waste streams into something useful? Turning two problems into one solution could help clean up our planet. Let's see how. Scientists are experimenting with ways to make concrete more eco-friendly by upcycling waste. They've tried adding plant fibers and nanomaterials to concrete, making it stronger and more durable. But these materials can be expensive, so researchers turn to plastics, specifically waste polystyrene. The big question, can we mix plastic waste into cement to create a better building material? Early attempts struggled to get plastic and cement to bond, like oil and water. The challenge was finding the right recipe to make these very different materials work together. That's where innovation comes in. A breakthrough came when scientists melted polystyrene into a liquid, then mixed it with CKD. The liquefied plastic coated CKD particles acting as a powerful glue. They didn't stop there. They added powdered waste glass and iron slag, both common industrial byproducts. This new recipe used up to 30% liquefied polystyrene, locking away huge amounts of plastic waste in each block. The process was energy efficient, requiring less heat and machinery than traditional concrete. The result, building blocks made almost entirely from waste, using a sustainable process. These blocks could help solve multiple waste problems at once. Scientists poured the mixture into molds and let it harden, creating strong, eco-friendly building materials. This wasn't just a new material, it was a new way to build. The final test, would these blocks stand up to real-world use? Let's find out. The new blocks passed tough tests. They were strong, even outperforming some traditional concrete. Thanks to the plastic, they were also lightweight, making them easier and cheaper to transport and use. Their insulation properties meant buildings would stay cooler in summer and warmer in winter, saving energy. Using CKD, polystyrene, glass, and slag, these blocks tackled 4 waste streams at once. Instead of polluting landfills and oceans, waste became a valuable resource. This reduces the need for new raw materials, protecting natural landscapes. It's a real-world example of a circular economy, reusing and recycling instead of just throwing things away. These blocks could help cities grow sustainably, with less pollution and lower costs. It's a win for builders, communities, and the planet. But the impact goes even further. This innovation shows how science can turn our biggest problems into solutions. By rethinking waste, we can build greener cities and reduce our environmental impact. Imagine skyscrapers and homes made from recycled plastic and industrial dust. Supporting science and staying curious empowers us all to make better choices for the planet. These breakthroughs prove we're not powerless. We can solve environmental challenges with creativity and teamwork. The journey from waste to building block is a powerful reminder of what's possible. It's not just about new materials, it's about changing how we see waste and our role in protecting the earth. That's a foundation worth building on. Hey everyone, welcome back to the Science Salah Lotfy Channel. If you've been following along, you know we're on a quest to turn two big waste problems, cement kiln dust and polystyrene foam, into something new and sustainable. Today, I'm breaking down the materials and the experimental approach that actually make this eco-friendly concrete possible. Ready to dive in? Let's go. First up, the stars of the show, cement kiln dust, or CKD, and polystyrene foam. CKD comes from the Torah Portland Cement Company right here in Egypt. It's usually a waste product, not strong enough on its own, but with a little help, it can be transformed. Then there's polystyrene foam, you know, the stuff in takeout boxes and packaging. It's 99% air, super lightweight, and takes forever to break down. So, the researchers dissolved this foam using regular gasoline. Yep, RON 92 you find at the pump. It sounds wild, but it works, and it's actually pretty affordable and scalable. Now, to make our concrete strong enough for real-world use, the team mixed in a few more ingredients. Classic Portland cement as a binder, finely milled iron slag, and waste glass. These help fill in the gaps and make the final product more solid and durable. So, how did they actually make these sustainable bricks? Here's the process. First, they grated polystyrene foam and soaked it in gasoline to create a thick, honey-like liquid. Meanwhile, CKD was mixed with water to make a paste. They blended the two together, poured everything into molds, and let it cure for a month. Covered first, then out in the open, letting any leftover gasoline evaporate. The mix: 90 grams of CKD, 63 milliliters of water, 10 grams of foam, and 20 milliliters of gasoline. They also tried adding different amounts of glass, slag, or cement to see what worked best. Testing time. They checked compressive strength with a heavy-duty Italian machine, measured water absorption and porosity with the Archimedes method, and used scanning electron microscopy to peek at the brick's inner structure. Finally, FTIR spectroscopy made sure the chemistry was on point. What did they find? This method doesn't just recycle waste, it makes lightweight, durable, eco-friendly bricks that could replace traditional ones. It's a win for science and for our planet. If you're curious for more details, check the article linked below. Don't forget to subscribe to the Science Salah Lotfy channel for more scientific journeys into sustainability. Thanks for watching. Today, we're exploring a breakthrough in sustainable building. The goal: create strong buildings while protecting our planet. Scientists are searching for eco-friendly materials that reduce waste and use resources wisely. Two major waste products, cement kiln dust, CKD, and polystyrene, styrofoam, usually end up in landfills, harming the environment. What if we could turn this trash into something valuable? Researchers discovered that mixing CKD with liquefied polystyrene, LPS, creates a new building material. LPS is made by dissolving polystyrene in a solvent, then blending it with CKD powder. The result: a CKDLPS composite, a building block made from two types of waste. This innovation reduces landfill waste and creates a material suitable for construction. The composite aims to be strong, lightweight, and a good insulator, helping buildings stay warm in winter and cool in summer. Using CKD and LPS tackles two problems at once: less waste and more energy-efficient buildings. This approach is a leap forward for sustainability. Instead of polluting landfills, these materials become part of our homes and offices. The CKDLPS composite can be shaped into bricks, blocks, or panels. Its insulating properties help save energy, reducing heating and cooling costs. By reusing waste, we're not just cleaning up, we're building smarter. This is how we create a healthier planet and a better future. Scientists continue to refine the process, searching for the best mix. Every improvement means less pollution and more sustainable construction. The journey from waste to resource is just beginning. With each step, we move closer to greener cities. Sustainable building isn't just an idea, it's happening now, and it's changing the way we think about waste in construction. Creating the perfect CKD-LPS block is like finding the right recipe. Scientists experimented with different LPS amounts: 10%, 20%, 30%, 40%, and 50%. Each batch was tested for compressive strength, measuring how much pressure it could withstand. Blocks with 10% and 20% LPS were weak, but at 30% LPS, the material reached its peak strength. Adding more LPS, 40% or 50%, made the blocks weaker again. Why is 30% LPS optimal? At this ratio, LPS acts as a perfect binder, filling gaps between CKD particles and creating a dense, solid structure. Too little LPS leaves gaps. Too much creates weak spots. The 30% LPS mix balances strength and durability. This magic number ensures the material is tough enough for construction. The right amount of LPS transforms waste into a high-performance building block. Scientists confirmed that the 30% LPS mix is the strongest and most reliable. This discovery is crucial for sustainable construction. It shows that waste can be engineered into valuable resources. The process is efficient and repeatable. With the right mix, we get a material that's both eco-friendly and practical. This approach can be adapted for different building needs. The compressive strength test is key to ensuring safety and quality. By optimizing the LPS content, we maximize the benefits of recycling. The result: a sustainable material ready for real-world use. This is how science turns trash into treasure. The journey doesn't stop here. Further improvements are always possible. But finding the best LPS ratio is a major milestone. It's a foundation for the next generation of green building materials. Strength isn't the only thing that matters. Porosity and water absorption are critical too. Porosity measures how many tiny holes are in the material. High porosity means more water can seep in. For building, low porosity is best to prevent water damage and mold. Scientists tested CKDLPS blocks for porosity and water absorption. The 30% LPS block had the lowest porosity and absorbed the least water. This dense structure makes it durable and weather resistant. Blocks with less or more LPS had more pores and absorbed more water. Too little LPS leaves gaps, too much creates weak, porous areas. The 30% LPS mix strikes the perfect balance. Past studies using solid polystyrene beads resulted in porous, weak materials. Liquefying the polystyrene first creates a much better binder, the result a stronger, less porous material than ever before. This innovation means longer-lasting, more reliable building blocks. Low porosity also means better insulation and energy efficiency. The CKDLPS composite outperforms older methods. Water resistance is crucial for real-world construction. The new process sets a higher standard for recycled materials. By controlling porosity, we ensure the material's longevity. This is a major step forward for sustainable building. The science proves that waste can be transformed into high-quality products. The future of construction is both green and durable. Could the CKDLPS block be even stronger? Scientists tried adding iron slag, another industrial waste. Iron slag's hard, gritty particles were mixed in, replacing some CKD. They tested blocks with 10%, 20%, and 30% iron slag. The best result came with 20% iron slag. Compressive strength increased significantly. Iron slag's sharp particles created a tougher internal structure, distributing pressure more evenly. But too much slag, 30%, weakened the block, since slag isn't as reactive as CKD. The sweet spot, 20% iron slag, 30% LPS, and the rest CKD. This mix is stronger and more durable than the original. Adding iron slag recycles more waste and boosts performance. The right balance is key. Too much or too little reduces strength. This approach shows how combining different wastes can create superior materials. The process is adaptable for various construction needs. Iron slag's addition is a win for both recycling and building strength. Sustainable construction benefits from smart ingredient choices. Next, scientists tested waste glass crushed bottles and jars, replacing some CKD in the mix. Blocks with 10%, 20%, and 30% glass were lighter but less strong. More glass meant lower compressive strength and higher porosity. The smooth glass particles didn't bond well with the LPS binder, creating weak points. However, lighter, more porous blocks can be useful for insulation panels. While not ideal for load-bearing walls, glass-filled blocks are perfect where low weight and insulation matter most. Every material has its purpose. Waste glass offers new options for green construction. This experiment highlights the versatility of recycled materials. The process can be tailored for different building needs. Using glass reduces landfill waste and creates specialized products. The key is matching material properties to the right application. Sustainable building means using every resource wisely. Waste glass opens new doors for eco-friendly design. To boost strength and stability, scientists added a small amount of Portland cement to the best CKD-LPS iron slag mix. Even a little cement made a big difference, filling gaps, improving chemical reactions, and reducing porosity. The result? Higher compressive strength and better water resistance. Portland cement acts as a powerful binder, working with CKD to create a stable matrix. This small addition unlocks the full potential of recycled materials. Over 90% of the mix is still waste, but cement ensures reliability. The right balance of new and traditional materials creates high-performance, eco-friendly composites. This approach is ready for real-world construction. Sometimes a touch of the old helps the new work even better. The result is a superior, sustainable building block. Innovation and tradition can work hand in hand. Let's recap the key discoveries. The best base mix, 70% CKD and 30% LPS, strong, dense, and durable. Adding 20% iron slag made the material even stronger. Too much slag weakened it, showing the importance of balance. Waste glass made blocks lighter but less strong, ideal for insulation, not load-bearing. A small amount of Portland cement boosted strength and water resistance. Each ingredient changes the material's properties, offering options for different needs. The process is flexible and adaptable. Combining waste with a touch of cement creates superior building materials. This research proves that recycling can lead to high-quality products. Sustainable construction is practical and effective. The right mix of innovation and tradition delivers the best results. Green building is within reach. These discoveries are more than scientific milestones, they're solutions for our planet. By turning waste into building blocks, we reduce landfill and pollution. Every CKD-LPS block means less trash and cleaner land and oceans. This supports a circular economy: reuse, recycle, and keep materials in use. Waste from one industry becomes a resource for another. Some mixes are perfect for insulation, saving energy and cutting carbon emissions. Lightweight materials reduce transport energy. Every improvement adds up to a greener world. Green construction is about making smart, sustainable choices. This research shows how innovation can solve real-world problems. The future of building is cleaner, smarter, and more responsible. We can build better cities and protect the planet at the same time. Sustainable materials are the foundation of tomorrow's world. CKDLPS composites are part of a global shift towards sustainable construction. Around the world, builders are rethinking materials to reduce waste and emissions. This method uses common waste, is simple to produce, and can be tailored for strength or insulation. The process is flexible. Add iron slag for strength, glass for lightness. Next steps: test long-term durability and scale up production. The science is solid. Waste can become a valuable resource. This is a message of hope and innovation. We don't have to accept a future of landfills and pollution. By embracing new ideas, we can transform waste into building blocks. Our cities can be strong, beautiful, and in harmony with nature. This research is about more than concrete. It's about a sustainable future. Human ingenuity can solve our biggest challenges. Together we can build a cleaner, greener world for generations to come. Hello, science fans. Today, let's talk about concrete, the backbone of our cities. It's everywhere: sidewalks, buildings, bridges. But making it, especially the cement part, pumps out a lot of carbon dioxide. Meanwhile, we're drowning in waste mountains of plastic and industrial leftovers like cement kiln dust. What if we could turn that waste into something useful? That's exactly what scientists are doing, creating new, eco-friendly concrete from trash. Imagine mixing old styrofoam cups and factory dust to make a strong, sustainable building material. This isn't just hiding trash, it's rethinking how we build, aiming for a circular economy where waste becomes resource. The stars of today's story: cement kiln dust, CKD, and liquefied polystyrene, LPS, or melted down styrofoam. Alone, they're just waste. Together, they're the start of a new kind of polymer concrete. Think of it like baking a cake, but with industrial dust and melted plastic where the recipe details matter. Let's dive in and see how this smart science could change the world. When scientists first mixed CKD and LPS, the result was promising but not strong enough for real construction. It also soaked up water like a sponge, not ideal for buildings. The fix? Add a bit of classic Portland cement, the super glue of traditional concrete. Researchers tested different amounts, 5%, 10%, 15%, to see what worked best. The more cement, the stronger and less absorbent the material became. This boost in compressive strength meant it could handle more weight and resist weather damage. Portland cement didn't just fill gaps, it reacted chemically, creating a denser, more unified structure. Think of it like weaving a basket. The cement threads pull everything tight, making it tough and water-resistant. This simple addition turned a good idea into a great practical material. The secret? The right mix and a little chemistry. With Portland cement, waste-based concrete became a real contender for building the future. It's a small change with a huge impact. Now let's see what's happening at the molecular level. To understand why Portland cement made the material stronger, scientists looked at the molecules using FTIR spectroscopy. FTIR is like a molecular fingerprint scanner. It shows which chemical bonds are present. When they analyzed the new concrete, they found evidence of calcium silicate hydrate, CSH, the powerhouse compound in traditional concrete. This meant the cement wasn't just a filler, it was creating new super strong chemical bonds. The result? A true composite material, not just a simple mix. FTIR proved the science. The waste-based concrete was chemically transformed, not just physically mixed. This deep understanding lets scientists fine-tune recipes for even better, greener materials. The chemistry is the key to strength. Next, let's see what this looks like up close. To really see the difference, scientists used a scanning electron microscope, SEM. The original CKD and LPS mix looked like a rocky landscape with gaps, weak points that let in water. But with Portland cement, SEM images showed a dense, compact structure. The CSH gel filled in the gaps, binding everything together like superglue. The result? A solid, unified material with no empty spaces. This matched the strength and water resistance test perfectly. The SEM proved that the new concrete wasn't just trapping dust and plastic, it was building a robust internal skeleton. Visual evidence confirmed the science. The material was now ready for real-world use. But could other waste additives work just as well? Scientists put other waste materials to the test, iron slag and ground waste glass, against Portland cement. Each was mixed with CKD and LPS, then tested for strength, flexibility, and water absorption. The results? Iron slag and glass made the material denser, but didn't create the strong chemical bonds needed. Only Portland cement triggered the crucial CSH reaction, making the concrete much stronger and less absorbent. The chemistry of the additive mattered more than just adding any waste. Portland cement was the clear winner, showing that not all waste is created equal in concrete science. This experiment set the direction for future research. Focus on additives that spark the right chemical reactions. The right waste used wisely can make all the difference. It's not just about recycling, it's about smart recycling. Now what about the plastic itself? Does it stay safe and stable in the mix? Let's find out. Scientists needed to know if the liquefied polystyrene, LPS, stayed stable in the new concrete. Using FTIR, they compared the plastic's molecular fingerprint before and after mixing. The result, the plastic's signature stayed the same. No breakdown, no harmful byproducts. The LPS acted as a stable, inert binder, locking in the waste without decomposing. This means the plastic is safely sequestered, not leaching chemicals or weakening over time. The concrete remains strong and durable, with the plastic acting as a reliable skeleton. This is a double win, safe for the environment and tough for construction. The process locks away plastic waste for good. It's a lasting solution for upcycling plastic. The integrity of the binder is key to long-term performance. The science proves it. This is a viable, sustainable way to recycle plastic. Now let's look at the big picture. This research is a game changer for the planet. It tackles two huge problems: plastic waste and cement emissions. By combining CKD and polystyrene, we turn trash into high-performance building material. This is sustainable development in action, meeting today's needs without harming tomorrow. Using waste-based concrete reduces raw material demand and lowers the carbon footprint of construction. It also opens new doors for local communities to turn their own waste into valuable resources. This isn't just environmental progress, it's economic and social empowerment. Trash becomes treasure, and everyone benefits. It's a cycle of innovation and renewal. Let's see how this could shape the future. This isn't just a lab experiment, it's a blueprint for real-world change. The construction industry needs greener, better materials, and this polymer concrete delivers. It's lighter, less absorbent, and perfect for sidewalks, sound barriers, and more. Every block made is a win: less plastic in oceans, less dust in landfills, less CO2 in the air. Science gives us hope and tools to build sustainably. The journey from plastic cup to building block shows the power of creativity and hard work. The materials we throw away are resources waiting to be unlocked. Building a greener tomorrow happens one block at a time. It takes bold questions, smart engineering, and all of us supporting new solutions. The future is built from today's trash, and that's exciting. Let's wrap up what we've learned. We've explored a new way to make concrete from waste, CKD, and melted styrofoam. Adding a bit of Portland cement made it strong and water-resistant, ready for real construction. Science tools like FTIR and SEM showed us how and why it works right down to the molecules. This isn't just a new recipe, it's a new way of thinking about waste and resources. With smart chemistry, we can turn pollution into solutions. The future of our cities could be built from yesterday's trash. It's creativity, responsibility, and science in action. That's how we'll build a better world, one smart block at a time. Hey everyone! Welcome back to the channel. Today I'm wrapping up our deep dive into some seriously game-changing, sustainable concrete research. Imagine if we could turn throwaway plastic and factory dust into super useful building materials. Sounds wild, right? Well, that's exactly what this study did. They took liquefied polystyrene, yep, the plastic clogging up landfills, and mixed it with cement kiln dust, which is usually a waste product from making cement. So what did the researchers actually find? First off, when they analyzed the mix under the microscope, they found a smooth, crack-free structure. That's a big deal for durability. Next, they tested how strong it was. Turns out adding more of that plastic actually made it stronger, up to a point. The sweet spot? 30% LPS. Go higher and the strength drops. But here's where it gets even cooler. By adding 15% of things like Portland cement, iron slag, or waste glass, they boosted the strength even more. We're talking up to 2.7 megapascals, enough for those inner, non-load-bearing walls. Plus, this mix is a champ at blocking heat and noise, which means comfier, greener buildings. What's the big takeaway? Instead of dumping plastic and industrial waste, we can upcycle it into eco-friendly bricks. It's cheap, practical, and so much better for the planet. If you're pumped about science that makes a real-world impact, hit like, share, and subscribe. And check the description for the full research paper. Thanks for watching. Let's build a smarter, more sustainable future together. Hello and welcome to the Science Salah Lotfy Channel. Today's episode is a heartfelt one. I've just finished sharing an inspiring piece of scientific work that shows how science can turn waste into value, transforming environmental challenges into real sustainable building solutions. Now, I want to take a moment to say thank you. Let's start with the incredible researchers who made this study possible. Deep gratitude goes to researcher Abeer El-Sayed, from the Chemistry Department, Faculty of Science, Al-Azhar University, Cairo, Egypt, to Professor Dr. Abeer Faheim and Professor Dr. Aida Salman, both from the same department at Al-Azhar University. And a special thanks to Professor Dr. Hosam Saleh from the Radioisotope Department, Nuclear Research Center, Egyptian Atomic Energy Authority, Cairo. Your work is a shining example of dedication, creativity, and scientific excellence. You haven't just found a new solution to industrial and plastic waste, you've paved a sustainable path for construction, not just in Egypt but everywhere. Thank you for your tireless efforts and for enriching our community with knowledge. Now, to you, our viewers, your curiosity and support make this channel what it is. I'd love to hear your thoughts in the comments below. What did you think of this research? Can it inspire new solutions in your own field? Let's start a conversation and build a space where science connects us all. Here on the For Science Salah Lotfy channel, I promise to keep searching for the best scientific stories from Egypt and across the world. Whether it's physics, biology, engineering, or chemistry, I'm committed to bringing you the latest research explained clearly and with passion. Once again, thank you to the researchers, and thank you to each of you for watching. With all my respect and appreciation, this is Professor Dr. Salah Lotfy, and this is the For Science Salah Lotfy channel, where science meets dedication, and knowledge has no borders. See you soon.